Hello guys, my name is Zhi. Today it's my great honor to introduce some of the efforts we have made to deploy video models efficiently in a scalable manner. Hopefully you will find this section helpful in some time. The outline of this particular deployment section is outlined as follows. First, the reason why deployment is a serious work. Second, what is the facts that cause deployment of video models being so hard? Third, I will walk you through some Jupyter notebooks and then play with a demo app on Jetson Xavier. Even if you are interested in other devices like mobile phone, we hope you can still benefit from it. Fourth, we will introduce a few things you can expect in the near future for deployment. Last but not the least, I will also talk about some takeaways in case you are totally bored and want to grab and go. To explain why deployment is important, we need to first clarify the idea of deployment for deep learning models. In order to start using a deep learning model for practical workload in commercial products or production service, it needs to be efficiently deployed into production. For example, you may train the model on cloud services, but deploy the model in a self-driving vehicle with completely different hardware and software stack. With such constraints, a model needs specialization, optimization, and conversion in order to run efficiently on different accelerators. And that question extends to the real problem. Why deployment is so hard for deep learning models, particularly for video-based models? The first thing that arises is the programming language. The majority of the deep learning frameworks use Python as the preferred development language thanks to its ease of use and dynamic properties. The similar story applies to, for example, R, Scala, that was loved by so many data scientists today. However, these languages may not be supported in the deployment environment. When it comes to deploying environment, things are getting very different. You may notice that the Python interface code that you are proud of may not even be supported on the devices. For example, iOS recognizes Objective-C or Swift. Android is using Java or Kotlin. A chip without Python interpreter is so common on the market. That means if you stick with Python code, you will not support either the iOS devices or Android devices. And the cost to rewrite these codes can be very high. Second, we are also slapped by the gap between powerful accelerators in the racks, for example, GPUs, and comparing with the battery-powered chips. It's inevitable that some heavy models needs modification before it can be useful on low-power devices. Portability and dependency is another issue. So if the deployment pipeline isn't scalable enough to support various devices without significant modification, then its value is highly doubted. For video, it's even more complex than the traditional images because videos requires a large amount of libraries to handle and imposing more challenges to maintain the dependency and portability across different environments. In fact, there's no way we can cover for all the failure cases of the deployment. Instead, I will introduce our approaches to handle the scalable while efficient deployment pipeline for ground CV video models. So let's take a look at the figure on this slide. Our deployment pipeline consists of two stages. First, the dynamic Python code to static graph representation. By performing inference once, MXNet is able to record in the entire graph representation because the operator are always supported by the backend, and the order of the execution will be fully recorded. Second, there are a couple ways to consume the static graph we just saved. It can either be directly used in online model serving services, or it can be directly consumed by the front-end languages supported by MXNet, which means there's all kind of language bindings, including R, Python, Scala, Perl, Java, C++, and etc. It can also be converted and optimized to TVM runtime library, or a third-party deep learning representation such as ONX. Today I will only focus on the MXNet and TVM deployment methods, but you will always find helpful resources on the internet for using the static graph representation in model server or either ONX. The Jupyter Notebook walkthrough section is a fully hands-on section. You can either watch the video and you can always try to grab the code on the GitHub and run the Jupyter Notebooks by yourself. Together with the Jupyter Notebook, we also prepared a compact example app to showcase the deployment using this approach. Don't worry if you don't have a Jetson device, because this kind of stack is usually helpful on all kinds of devices. Okay, in this section, I will walk you through a complete example so that you can build your own video classification app on a Jetson device. This deployment hands-on section will cover three major parts. First of all, I will introduce a Jupyter Notebook for high-level interaction with deep learning video models. The Jupyter Notebooks consists of video model inference inside the Python environment, model export to MX runtime so that it can be executed in C++ or Java. I will also introduce the export method for TVM, which is an end-to-end deep learning compiler stack designed for CPUs, GPUs, and specialized accelerators. Second, I will try to build the TVM-based video classification app step by step with the help of Tcode library to read the video files and convert them into frames. Finally, I will demonstrate how this tiny app we just built is able to perform human action recognition tasks efficiently using the CUDA compute power on Jetson devices. Also keep in mind that TVM supports a broad range of accelerators not limited to CPU, GPU, ASIC, FPGA, and etc. So with slight modifications, we will be able to cover tons of different hardwares without significant rewrite of code. Okay, first thing first, let's get this started with the Jupyter Notebooks. We will have three Jupyter Notebooks here. Let's get to the first one, which is for Jetson Inference using Python. Keep in mind that the environment of this Jupyter Notebook is running on a Jetson Xavier, a relatively powerful Jetson device. But you will be expecting that even a Jetson Nano can run this tutorial smoothly without any issue. So this Jupyter Notebook walks you through the entire pipeline for inference of the video classification model. First thing we need to do is to make sure the dependency is fully installed. You will be able to find the detailed instruction for installing these dependencies on this GitHub repo. So we need the MXNet as the deep learning framework for inference, a GlonCV package for model definition, and the model zoo, and also the decode library for reading the video frames out of the packed video file. The pre-processing is a little bit different from the image classification, since we are doing with multiple image frames out of a video. However, the decode has enabled the Pythonic way to read frames from the video file. Here, as an example, we first grab a test MPEG-4 video file and load that with the decode video reader. We then define the frame range to be loaded. This thing, since we are dealing with the slow-fast network, we are trying to get the fast frame ID list and a slow frame ID list. For the fast video stream, we would like to sample it with interval of 2, and for the slow stream, we sample it with the interval of 16. Finally, we concatenate these two streams and form the slow-fast streams. The video data can be loaded with the function getBatch with a single line of code from the video reader. By printing the clip shape and clip length, we get a better understanding of how this thing are working together. So finally, we have the clip shape of 256 by 454 with the entire clip length of 36, which consists of 32 fast frames and 4 frames in the slow stream. After grabbing all these video frames, we'll be able to perform the transformation so that it becomes the input to the network itself. So this validation transformer we define here is for performing the inference part. We define the input frame size to be 224 with the mean and standard deviation values here. After that, we stack the input clips into the first axis and try to reshape it to the preferred input shape of the slow-fast network. If you get confused about how these frames are stacked together, we can print out the shape of the input. Here, 3 is the original RGB channels, and we stack the 36 frames at the second axis here, or actually the third axis here, so that it becomes the perfect input for the slow-fast network. Next step is to load the slow-fast network. We specify the model name and trying to get the model out of the model zoo in GlonCV with pretrain equals true, we will be able to directly download the model files from the S3. And here we specify the context of the execution to be on GPU, and 0 indicate that we are trying to run it on the first GPU, even though it only has one. So after this operation, we finally have the entire model sitting on the first GPU and ready to go. The next step is to run the inference. We will be able to grab the prediction from feeding the network with the multi-dimensional ND array and trying to copy, well, remember to copy the data into the GPU before doing the inference. And after that, we'll be able to get the prediction by performing, for example, top 5 sorting on the indices. So the best prediction we get is the upscaling, perfectly aligned with our test video. So that's it. With a couple predefined processing and loading, we'll be able to run it perfectly in the Python environment. Next thing up, we'll be able to jump to the deployment. So in the previous Jupyter Notebook, we have already seen the Python way to do the inference. However, in some situations, we do not have Python environment on the deployment devices. So in this example, I will show you how to efficiently export the models into a static representation, so you will be able to use them everywhere. So you can see this is super simple example here, only consists of 5 lines of code. And in order to perform that, we first import the dependencies of the Golang CV and trying to get the model just like we have done before by specifying pre-trained equals to true and the name of the models. And also we are using the GPU to doing the final inference part, because in order to let the framework understand what we are doing, the network has to be inferenced once and generate the entire, the complete network definition before we can save it to the disk. Here we also provide an export block function to generate the finalized network representation. Okay, enough talk. Let's run this example in line. And also keep in mind that the layout is very important here, because it specifies which one is the original channel dimension and which one is the temporal space. Because usually the image tasks don't have the temporal space, you will have another batch layout here. But never mind, it's already finished. The generate results we can see from here is the slow fast blah 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 dot parameters file, which contains the trained parameters, and also the JSON fire, which specifies the network representation. If you're interested, you can also print out the JSON file. It has some nodes information about every single layer in the network. So once you have the JSON file, it will be able to be parsed in whatever front-end languages that MXNet supports. So at this level, you will no longer need Python to do the inference. And that's it. The next step is you can use these parameters and the JSON files in C, C++, Java, and etc. with MXNet runtime. Okay. The last Jupyter Notebook I would like to introduce is very important because it is the prerequisite for running the TVM-based video classification deployment example. This example will be very similar to the MXNet version with a slight difference in the pre-processing pipeline and also the output shape. In this example, I will be using a very tiny network a ResNet 18-based TSN model trained on Kinetics 400. Let's first rerun all this code and let's get through it step by step. The first thing we need to make sure is we have the TVM installed. For instruction of how to compile and install TVM on the devices, you can refer to tvm.ai and check out the installation part. And after all these requirements are met, we can start downloading the pre-trained model from Gurong CV Model Zoo, as well as the injection parts for the data preprocessing pipeline. So this part is exactly the same as the previous Jupyter Notebook. I will skip this part. And for the preprocessing, it's very interesting because you can inject the preprocessing pipeline into the network itself. Well, if you are wondering why we are doing the injection of preprocessing blocks into the network, here's the thing. Imagine that after deploying your model into some format that can be fully interpreted by the inference engine, and you have raw pixels loaded into input tensor. At that time, you will notice that without a proper processing block written in deployment code, you won't be able to perform inference correctly. Think about dealing with image normalization in native C++ or Java code. You will appreciate the embedded processing block we have just injected here. With the processing block injected, the input can be directly fed into the network without extra processing. Not only simpler to handle, but more efficient because we can fully utilize the optimization of TVM operators and scheduling here. In fact, we are doing very simple processing here by subtracting the mean values and divide by the standard deviation values. This is the only requirements we needed here. And also the mean and scaling coefficient will be saved to the network itself. So you don't have to worry about carrying the mean and the STD values to the inference part. So again, similarly, we are utilizing the export TVM function here with a little bit modification because TVM now support generating the code for different targets such as CUDA, LLVM, OpenCL, and etc. We also specified optimization level to 3 in order to get some appreciated optimization on the graph level and optimization level. This is some verbose knowledge that TVM is telling us. It says some of the best configurations searched is not available for this new workload, but don't worry about it. It's just telling us there's potential optimization we could get from whether we can use Auto-TVM to tune the network. So at this level, we already have the model exported to TVM, and the last thing we would like to make sure is we don't lose the track of the class names. So we open up a synset file and trying to write the entire 400 classes into that text file so we can reuse that later. So here is what we have after export to TVM. Okay, so similarly, the params fire is used to store the pre-trained weights of the network. The JSON Fire is used to represent the entire network. The shared library is the TVM's selection of operators and runtime for inference. And the SyncStat file we just write is a pure text file with 400 lines of class names for this kinetics data set. And so that's it. This is what we need to export the network for inference. Okay, now I will try to build the standalone classification app step by step. So let's open up a terminal, and we will be able to following the build process here. I assume the tutorial is using Jetson device with Jetpack 4.4. First thing we need to do is to install the system packages. A lot of these dependencies are required by the FmpEg and the video reading stuff. So we will go get the updated Once done, we can install the required dependencies. Okay, looks good. And this step is very important to make sure we have all submodules updated recursively. And now we can enter this demo repo and try to create a build directory and use CMake to build the app. Okay, I'm making a mistake here. It's into this folder. The CMake will check all the required dependencies and try to, after it finishes, we can build the entire classification app. The first step of the build is to compile the decore library because we rely on decore to read the image frames out of the video file. So relax and be a little bit patient here because the CPU isn't super powerful on these Jetson devices. The build took roughly 3 to 4 minutes. So now we have already have the video classification app ready. By checking the usage info of the video classification, we'll be able to get the tips of how to use that. First thing first, let's get some example videos. We can grab, for example, the pancake video here. So the video classification app expects input video file and also the model name prefix, so it can properly load all the dynamic library, parameter fire, JSON fire, and also expects the ID of the GPU. You can specify GPU ID to be -1 and to tell the app do not use GPU, use CPU instead. But here is since we have a powerful GPU on the Jetson, we can fully utilize that. So in order to run the demo app, we can specify the video file as well as the generated TVM. The name of the is ResNet. ResNet 18, and don't forget to specify the GPU ID. From the verbose information, we get the idea that the app successfully read 13 frames out of, for example, we can take a look at what the original video looks like. Let's use FMPAG to check how many frames we have. So overall, we have 310 frames in this example frame. And also, let's take a look at the output. That is because we read the input every 25 frames. So overall, the elapsed time for the inference part is 256 milliseconds. And the final prediction is classified to be flipping pancake, which perfectly aligns with the test example video file we have. So in order to illustrate why and how we example the input frames out of the video file, we can modify the app a little bit. So let's see, there is the classification source file. We sample the video file with 25 at the interval of the frames. So let's change it to every 40 frames and build the app again. Let's rerun the inference code. Now this time it sampled 8 frames from the input video. But again, the prediction looks again very good. Another thing I want to mention here is the inference code, it only works for targets, which means if we specify CPU as the workload, it won't successfully, this indicates that CPU is not a valid device. Here we can do a slight change to make it work. Let's go back to the TVM example here. let's switch every single use of GPU to CPU, and again change the target from CUDA to LLVM. It tells the TVM to use LLVM as the backend code generator. Okay, this time let's try GPU first. It's telling us that the device does not satisfy the constraint. Okay, then CPU at this time. We can see it runs successfully with the same prediction as the GPU version. Well, it's actually 7 to 8 times slower than the original GPU version, because the CUDA device on Jetson Xavier is much faster than the CPU. Okay, that's pretty much what we need for the deployment example app. And also keep in mind that the size of the app itself is only 800K, way smaller than a traditional deep learning framework. So hopefully you'll find the deployment example I just talked about very interesting and helpful. Here's several things you can expect in the near future. The first thing is the deep TVM deployment with 3D convolutional neural networks. It's a pity that we haven't fully rolled out the 3D support for TVM deployment. The next thing is the int8 quantization for Guang-CV video models. With the help of quantization, we can significantly reduce the size of the model weights as well as the inference time, as long as the accelerator support the int8 acceleration. And third thing is the Guang-CV video model zoo. We have collected a curated list of models specially optimized for individual devices. Okay, finally, some takeaways for the deployment. First is you need to think twice about deployment before you develop these models. Redesign model or rewrite the code for deployment can be very costly. In this case, we use TVM to generate device-specific library, which is lightweight and efficient. We have also shown that switching different accelerators using TVM is extremely simple. You only need to specify the code generator target. For example, CUDA, OpenCL, LLVM. Second, we now have decore library to deal with video inputs as straightforward as images. You will be able to access the sequential image frames or either sample the image frames from the video directly without introducing tons of code to handle these videos. In case there's CPU, GPU available at the same time, for example, the Jetson Nano, Jetson Xavier, make sure you figure out which one to target. For example, the GPU on the Jetson Xavier is much more powerful than the ARM CPUs. So instead of generating the LLVM code, you can try the CUDA code generator by TVM. And finally, the materials for this tutorial are all open source and available at the following GitHub repo. So hopefully you will be able to consume it and modify it for your needs. Thank you and have a good day.